Hi, good morning. Welcome to the third cryptography lecture in InfoSec. Today we are going to make a big jump in the type of cryptography that we're talking about. And in particular, we're going to switch to asymmetric cryptography. So if you remember...
previously on DOS.
Address 9.
Windows out like this. Okay, so if you remember last week or the last 2 weeks, we had a look at symmetric cryptography. So we looked at different goals, on the one hand integrity and on the other hand confidentiality, but we achieved all of that either without keys in the case of hash functions or with a symmetric key. So where both communication partners had exactly the same key and could use it to encrypt and to decrypt. And today we want to talk about a different kind which can also achieve confidentiality and integrity, but it only does so in one direction. We'll get to what that means exactly a bit later, but there are three main cryptographic schemes and primitives that we want to look at. So the first scheme is a key exchange scheme for setting up communication. The second one is for integrity, it's called signatures. And the last one is for, or the one that's not clearly mentioned here, but that's about encryption, is about confidentiality. What this last part means here is that we are going to look both at the schemes and at the underlying primitives, so at the reason for the security of these schemes, so the asymmetric primitives. And we're going to see that they are very, very different from what we've seen in the symmetric world. And next week we still want to have a look at how we can get this into practice. So how all of these schemes here are actually used, what can go wrong, and topics like that. So let's have a slightly closer zoom on last week's lecture. Here we talked about encryption schemes, and in particular two different types of those, namely pure encryption schemes, which only protect confidentiality, where both people could encrypt and decrypt, but they couldn't verify if maybe an attacker had changed the message in transit. And we looked at a way to solve this called authenticated encryption, which encrypts and adds an authentication tag. And here also both parties can encrypt and decrypt. Good morning, Hexa. But they additionally can check who sent the message, so that it's definitely from one of the owners of the secret key. Okay, and there's a third type of encryption that we've mentioned last week, but that we're only going to have a look at this week, and that's public key encryption schemes, also called key encapsulation schemes. So here the idea is that anyone can encrypt the message, but only the owner of the key can decrypt. Okay, so let's have a look at how we build these two things here. So we said that there are two layers to such a construction. The bottommost layer is the so-called primitive. So a primitive is the smallest building block that still provides security. If you break it apart in any way and look only at part of it, this part is not secure. So typically, if you break it into parts, you would call these parts rounds. But rounds are really just simple operations that by themselves cannot provide security. They only become secure once they are used together. The way they are used together is by combining them with round keys generated by a round key schedule. Okay, and once we have such a primitive, the primitive is nice, so it's like an engine that can drive our car, but we still need to build the car around it. In other words, we need to make it usable, to actually process messages that are arbitrarily long in a secure way. And this is where mode of operation comes in. So here I've illustrated one. It's essentially a recipe how to use the primitive, so the engine, to get something done. Getting something done in the case of this picture would be to authenticate both the associated data and the message. This is what the top part does. And to encrypt the message to a ciphertext, so that you then send the ciphertext and the final verification tag that allows the recipient to check that all went well. Okay, so to have a closer look at that, let's have a look at your first questions and the recap quiz. I have to say I had a look at the questions in advance and they seem to be very related to the KU. So we can't really clarify questions regarding the exercises here. Please ask them in the afternoon in the question hour. So in particular, the first question here, which doesn't want to appear just yet, but maybe it will if I reload. Let's see. Yeah, so if you get a checkmark on the test system, blah, 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 I read test system, please ask that in the afternoon or on Discord. Same for this one here, question regarding the exercises. Let's have a look at this one. This seems to be related to the lecture. So have you seen any symmetric crypto approach which provides just authenticity or integrity, but not both at the same time, or did they always go hand in hand? They always went hand in hand because if we talk about message authenticity, then authenticity always implies integrity. So authenticity means I can verify who sent this message, and integrity means it wasn't modified. And if anybody would be able to modify it, then it would no longer be authentic. So authenticity of a message implies its integrity. If we look at it the other way around, so if we look at just integrity, you could argue that hash functions by themselves just protect integrity, because they don't really tell you anything about who computed the hash, because everybody can compute the hash. So I would say a hash function just does this part here. But you can use it together with some other scheme to again get both. Okay, but really it's a bit of a fine line, and it also becomes a bit more confusing if we talk not just about message authenticity, but about entity authentication. Then we're talking about something else entirely, because if we are talking about entity authentication, that's like a login, integrity plays no role, just authenticity of the request. Okay, then let's get back to the slides. No, not the slides actually, but the recap quiz, which we have again. So please join. I'll give it a few seconds again until you're all here. And when I look at the viewer count and at the playback count in my control window, it looks like some of you have a bit of a delay and are watching this in playback, so with a few seconds delay. So maybe you want to check that you are live. Now would be a good time to do that, if you're just a few seconds behind. Okay, so this looks pretty stable. Let's assume everybody's here, and I hope some of you have switched from lagging a few seconds behind to being live. Let's have a look at the first question. Which security property of the message does authenticated encryption protect? A, privacy, B, collision resistance, C, confidentiality, or D, anonymity? Yes, you're absolutely right. It protects the confidentiality. Additionally, it does protect the authenticity and integrity, but we haven't listed them here. Since it's extremely bright in here, I'll have to make a little noise for a few seconds while you answer the next question to adjust the lighting. But let's look at the next question right away. Looks like the camera is really having issues here. So, which statement about nonces is false? That they must always be kept secret, that they are a number used only once, that reusing them can reveal some patterns, or that they can often be a counter or a random number. Yep, that's correct. So indeed, they do not need to be kept secret. So there are a few protocols which treat them as secrets, including TLS, but it's not necessary. So they can be public numbers, and in particular, they can be something like counters or random numbers in many cases. Okay, let's look at the next one. So, let's see. Which one is the lowest layer in the crypto stack? Is it the protocol, the primitive, the scheme, or the mode? Yes, indeed, it's the primitive. So that's the atomic building block, we say. The mode describes how to use them, and the scheme is the result of combining the mode with the primitive. So this is like the construction model for the car, and this is the actual car model. And the protocol then uses this entire thing. So a protocol would be something like the Straßenverkehrsordnung, so the traffic rules, or something like that. Okay, question 4 out of 5. Which of these is not a design principle for block ciphers? To repeat a round function r times, or the key alternating construction, or the discrete logarithm, or the substitution permutation network. Majority is again correct. So the discrete logarithm is a mathematical function or problem that we're going to look at today, but it has nothing to do with block ciphers. I see that some of you picked a substitution permutation network. That was maybe a bit of a difficult question because I'm not sure if I mentioned the term clearly last week, but the substitution permutation network describes a construction similar to the AES that we saw. So substitution is the S-box and permutation is the mixing layer. So I'm sorry if this caused confusion. And the first two, these are indeed the two main principles that you find in almost all block ciphers. Last question, last chance to get some points. What was the goal of the AES competition? Was it to find the fastest hash function, or to replace MD5 hashing, or to replace NIST, or to replace DES? Indeed, it was about replacing the old data encryption standard. The new one is called AES, Advanced Encryption Standard. NIST is the organization that held this competition, so it's called sometimes the NIST AES competition. It's the National Institute of Standards and Technology in the US, and it's responsible for making sure we have good crypto that's used all over the world, in fact. Replacing MD5 is a good idea because MD5 is an old and broken hash function, but this was already done first with the SHA-2 and then later with the SHA-3 competition. And finding the fastest hash function was not the goal at all, even though speed does play a role in the evaluation of such schemes. Okay, let's have a look at the leaderboard. Okay, congratulations CC, you were the fastest. And I see Wolfgang Slani is also who is joining us every week. Okay, so let's have a look at the outline for today. And let's hope the camera starts recovering from its focus issues. Okay, so what's the plan for today? The first, half an hour or so, is going to be a bit mathematical. So first we have some non-mathematical topics, so we're going to look at what the goal for today is and why we need something in addition to the schemes we already have. So at some goals and applications and problems that we have if we have only symmetric cryptography. But then we're going to need to do some recap of stuff that many of you, but probably not all, have already heard. So in particular, in all of the rest here, we are going to need what's called modular arithmetic. So that's a kind of computing using the modulo operator, but it's a bit more than that actually. And I guess many of you heard about this in discrete mathematics, but some of you didn't have that. So in particular, I think the ICE people don't have that anymore. So for this reason, and probably because many of the others also forgot all about it, I'm going to repeat that. So it's going to be a bit mathematical. And afterwards, we're going to see different ways of using these things. First for key exchange, then for encryption, and then for signature schemes. And all of these schemes are based on so-called hard problems. And these problems are based on the arithmetic that we're going to look at. Okay, so let's have a deep dive right into this background, I promised. I see there is a question. Let's maybe handle that first. My phone doesn't know about it yet, but let's see. The question is whether you should remember things like what was replaced for the exam. I think it's a good idea to know about the DES, knowing that it's not good for use anymore, but recognizing it. It's not the most important message I try to get across, so it's not going to be a major part in the so I don't think I've ever asked it in the exam before, if I remember correctly. But I have to say that I do have always some exam questions that are very similar to the quiz questions I have in the beginning. So you should still feel like you're able to answer those. Of course, there are also more explanation questions where you actually explain stuff and give a text description, but there are also a few of these checkboxes things. Like what I find really important, what I always ask about is which security properties different schemes give you. What kind of key you have, so if it's asymmetric, symmetric, this kind of stuff. So that's a much bigger part of the exam. Yeah, and for the schemes that I do explain here and give an algorithmic description, you should definitely know the name. So you should know what the AES, for example, is and what, for example, its round functions are called. Approximately. So I'm okay if you slightly, if you have some small bugs in the description, but it should be recognizable. Hard problems or hard problems? Well, maybe for some people it's both, but for the most part we're talking about hard problems. Okay, good. Let's then indeed go into the background. And let's hide the Q&A, which I did, but somehow Menti didn't get it. Okay. So, what's the main limitation of the schemes we've looked at so far? So in particular, the limitations of symmetric cryptography in general. The main issue that we have is that we need this shared secret key. And to distribute this is a really hard problem. So it's already difficult if you just look at one pairing of people, but what if you look at an entire network? For example, you have a network of n users and they all very often need to talk to each other. Then you need to exchange a total of n choose 2. So that's n times n minus 1 divided by 2 key pairs, because each pairing needs their own key pair. So in other words, every participant in the system also needs to remember one key for every other participant in the system and get to exchange this in the first place. So this would make something like confidential communication in a big company really more or less impossible, not to even start talking about securing the entire internet. So how would you ever connect to a website you've never talked to before? You would have no shared key. So this would be difficult. And another thing that is a limitation of symmetric cryptography is that it's only suitable for symmetric trust relationships. What do I mean by that? It means that users always trust each other equally. So both communication partners trust each other. So in particular, it doesn't support talking to anybody new that you don't trust yet. And on the other hand, there are some cases where you maybe do not trust each other. One such example is if you think of a contract. So if two people try to come up with a contract, we would want it to be authentic in some way. So we would need to be able to verify that both of them agreed to it. But if they both have exactly the same key, they could, for example, both compute a MAC or a hash or so of this contract, and it would be meaningless because one party could do it alone because they have access to the entire key material. So something like non-repudiation isn't possible with symmetric crypto. What's non-repudiation? This is in German Nichtleugnbarkeit. So as a sentence explanation, it means not being able to deny that you have sent something. So for example, we would not like a person to be able to deny that they have signed a contract because they are bound to it. And this is something that's difficult to achieve with what we've seen so far. And that's where asymmetric cryptography enters the field. So on the left-hand side here, we see the symmetric world. So we have two people, they trust each other, so they're in their own secret bubble, and they can encrypt messages to each other and ensure the authenticity by using a MAC, for example. In the asymmetric system, the security box only contains the owner of the private key, but everybody else can interact with them. So for example, by sending them encrypted messages that only Alice can decrypt. Or Alice can sign something like a contract, and later everybody can verify that it's correct. And nobody else can produce this signature, only Alice. So we have a sort of user-centric perspective. This is more a group-centric perspective. So you have the group of insiders and you have outsiders which have, which have no rights at all. Here you have one user, they can do everything, and the other people cannot do anything. Or can do something, but not everything. So which schemes are the most widely used ones in this category? Well, the first one is the one that solves the first problem that we saw, namely the key distribution problem. So these are called key exchange schemes. And the idea is that Alice and Bob communicate together, and after finishing this procedure, they have agreed on a new symmetric key. So afterwards, they can use the symmetric key for authenticated encryption, for example. Typically, both of them have some influence over the key, and both of them, after completing these steps, know the key. But nobody else who watched the entire conversation can do the same. So that's the magic part. Then we have encryption schemes, which are also very often used in the key context. So here the idea is what we've seen on the previous slide, namely that anyone can encrypt a message, its confidentiality is guaranteed, and they can send it to someone who can decrypt it and use the message. And typically this message is something very short, like a symmetric encryption key. So this is why these schemes are often used in place of key exchange schemes. The difference is that in a key exchange scheme, typically both people influence the key. In this case, one party would choose the key and send it to the other party, and then both know it. But only one has control over it in the sense that they have generated it. And finally, we need to do something about the authenticity, and that's where signature schemes come in. So here, Alice can authenticate a message and everybody can verify it. So what are some applications of all of this? For digital signatures, these are really very varied. So some of the most widely used ones are, for example, websites, which use this HTTPS technology, which means the TLS protocol. And there, for example, you need to verify the authenticity of some messages that you get from the server, so the service certificate. This is done by a signature. You can also add a signature to your emails, and by that I don't mean typing your name under it, but actually adding a cryptographic signature. For example, we're using PGP. It's also done for software signing. So for example, software vendors sign their software to allow the end users, all the end users, to verify the validity. This is a context where you could also use Max, so it depends a bit on what the exact setting is. But if you download, for example, a Linux distribution, you very often have access not just to a hash value of the image, but also to a signature over the image. It's also used in digital currencies and in Austria quite a bit in electronic signatures. So, for example, in the handy signature, mobile signature system. Which is, at least in my daily life, used quite a lot. Okay, so that's about signatures. How about key exchange and encryption schemes? Well, they are used in almost all communication protocols that are for online communication, which includes TLS for websites, or IPsec for protecting VPNs, or SSH, for example, which you might use to connect to different machines and do some stuff there. So these are all using key exchange schemes typically. They might also use asymmetric encryption schemes for key encapsulation. So for encrypting a key, sending it, and then having a shared secret key for symmetric crypto. It's also used in SSH. This is also what you can do for email encryption, for example, because one difference between email encryption and these here is that here both parties are online at the same time. They can actually talk to each other, exchange messages live, which means you can use a key exchange scheme. But in an email, that's not the case. It's not the case that both people, the sender and the receiver, are online at the same time. So the communication only goes one way, which means you also need a key agreement scheme that works one way, and that's encrypting the key. Okay, so that's it for the motivation and the goal that we set ourselves to achieve today. Now we need to do some work to get there. And this work includes some math. And because I don't know exactly how many of you have done how much so far, I have prepared a little poll. To ask you how much you know already. Let's see how long it takes Menti to realize I want something from them. Here we go. So what I'd be interested in is to know how well you know first the mathematical basis, so whether you know what the modular operator does, I should hope so, whether you know what modular arithmetic, so computation mod n, using this thing is about, and if you happen to already know some of the encryption schemes here. So let's have a look at that. Okay, it looks like I hope that most of you seem very familiar what the modular operator does, but less familiar with doing arithmetic with it. That's approximately as I expected. It looks like very few of you feel like they know about a lot about RSA encryption. I think this is usually covered to some extent in discrete mathematics, but I'm not sure how much to what extent it was covered in your year and whether you actually had that course. It actually seems to my surprise that Diffie-hellman key exchange seems a bit more well known, but maybe that's due to the very, very small number of samples here. So only 2 samples. Apparently not everybody reached the end of the poll. Okay, but that already gives me a good feeling of your state of knowledge, and it also shows to me that still some people are a few seconds behind apparently. Okay, so I'll try to divide my time accordingly and spend more time on explaining this, still sufficient time on explaining this, and only very short time on explaining this. Okay, so back to the slides, and for one short look at the questions. So there is one application question on the George Sparkasse app. I'm sorry, I can't really comment about software that I haven't had a detailed look at, so I can't answer that for you, unfortunately. So somebody says that ICE students don't have discrete math. Yeah, that's what I expected. So it's a bit unfortunate for this course here, but I understand that your curriculum is already filled up to the brim with other stuff. So that's also part of the reason why I repeat things here. And then there is a question about 2 different email protection systems, namely PGP, which is sometimes also known as GNU-GP, PG, and SMIME. both of which have their advantages and disadvantages. So let me very briefly comment on that. So PGP is a system that works on, it's a sort of a peer-to-peer system. So the way this works is you can encrypt emails to somebody who has a PGP key, and they publish the public key on the internet. And in order to get some trust that this is actually the key of the right person, people sign each other's keys. So you need to first get a sort of trust group who says, yeah, that's really Maria's key, before everybody else trusts Maria's key on some key pool online. So that's nice because it's a sort of grassroots thing, so you can just join without much effort. There are, however, a few downsides. So in particular, the original PGP system is pretty old and uses some pretty dated understanding of cryptology, I'm afraid to say. So I wouldn't describe it as a model of how to properly use cryptography. That's a bit of my issue with it. SMIME uses a different system, so it doesn't have this peer-based trust. From this area, you might know the keyword of key signing parties. That's where you meet up, you show each other your ID cards and say, this is my key, and then you all sign each other's keys to get some trust to get started with. SMIME is different, it's based on certificates. So you need some authority to actually issue your certificate that says, this is Maria's public key. You don't need any peer group to say so, but just one authority. So it's more hierarchical and authority-based, which has its advantages. So particularly in, for example, a company system, it totally makes sense that every employee is issued an SMIME certificate and can sign their emails with that. Because there's a clear authority, that's the company IT system. It's more difficult to get access to maybe in some other contexts. And some people also just generally dislike the idea of some sort of centralized trust. This is decentralized trust, this is centralized trust. But I do believe that in practice it really has a lot of advantages. So that's my comment on that. Use whatever suits you. This is more easy to integrate in some email clients. It depends a bit also on what your client supports and what your contacts support. And because this is more used in a sort of officially or business area, this has received more support recently. But both is really fine. So, what about mobile signatures? Are they trustable? Yes, they are. They were actually developed at the IAK many years ago, and still are continuing to be developed, or partly at IAK. Nothing could happen. Well, there are a few things that could happen. I don't want to go into too much detail, but it's not the fault of the crypto. So in particular, if you attach a mobile signature to a PDF, for example, you cannot modify the PDF anymore. So the signature will not validate anymore. So the authenticity and integrity is guaranteed in that respect. But of course, there are still a number of things that could happen, like your phone could be totally compromised and could show you some fake PDFs instead of the real ones. And well, if you assume a very strong attacker, you could come up with something, which holds true for really any sort of IT security system. But generally, it's a very good and trustworthy approach. Okay, so let's talk about stuff you might want to know. So the previous knowledge that some of you have to some extent, but not too many feel really confident. So what do we mean by modular arithmetic? The main thing is that we're doing computations modulo a number. So for those one or two who didn't click full confidence about the modulo operator, what does it do? Well, if you take one number modulo another one, the result of the computation is the remainder after division if you would divide the first by the second number. So for example, 10 modulo 3 is 1 because 9 is divisible by 3. So the remainder by division after division by 3 is 1. And if we do all our computations modulo a fixed number n, which is called the modulus, then we're doing modular arithmetic. Now, since we always reduce by n, this means we only really care about these numbers here, 0 to n minus 1, because any larger number or any smaller number can be mapped to this range. And for this reason, we group all the numbers that would be reduced to the same number into a class. And we say that these are the representatives of the class. But in practice, on paper, we just write them as numbers, and we don't care about classes or representatives or anything. And two integers which would be in the same class, so for example, modulo 10, 0 and 10 would be in the same class. In that case, we call them congruent modulo m, using this writing here. So this is a sort of equal signs, but where the equality isn't true for the original integers necessarily, but just after applying mod n to both sides. So if we have an equation and we write mod n at the end, with usually a bit of spacing, and then we mean all of this computation is modulo n. So it doesn't just refer to b, it's not like an operator anymore, but it's a general statement about which data type, so to say, we're speaking about. So it's really that a and b are considered as a data types modulo n. Okay, so let's have a look at a number example that we're going to use on the next slides, and that's computing modulo 11. So modulo 11, we have 11 classes, 0 to 10, and all other integers can be mapped into one of these classes. So for example, the class 0 also contains 11, 22, 33, and so on, but also minus 11, minus 22, and so on. And similar, the class 10, for example, also includes, so that's 11 minus 1, so it also includes 2 times 11 minus 1, 3 times 11 minus 1, and so on. But also 0 times 11 minus 1, or minus 1 times 11 minus 1, and so on. So in particular, you notice that if we look at the negative numbers in the class aren't just minus the positive numbers, but they are chosen such that there is this fixed difference of 11 between all numbers. Okay, so these are the 11 classes we have. We can also, so it's often convenient to write them as a sort of circle, because after you go through that, after 10, you would go to 11, which is equivalent to 0, and so on. And we try to do all our computations such that all results are also just in this set. So in particular, please never ever have any, for example, rational numbers or irrational numbers when you are doing computations modulo n, like dividing. You should only ever end up with integers, and in particular, with integers in these classes here. Okay, what's the convenient way or the convenience of doing that? Why do we bother computing modulo a number? Well, the first reason is that we have computers which have a finite instruction word size, so we are somehow limited to doing finite computations. And doing computations modulo a number has some very nice advantages. In particular, if that number is a prime number, but also in other cases. And in fact, what your CPU already does implicitly, if you have, for example, a 64-bit ALU, so arithmetic logic unit, then all of the computations are kind of cut off after 2 to the 64, right? So you're actually already doing arithmetic modulo 2 to the 64. But in cryptography, we don't like 2 to the 64 so much. We like other moduli much better, in particular prime numbers. Because if you do computations modulo prime numbers, you get some very nice properties. But even for other composite numbers, addition works nicely. So in particular, it works so nicely that we have some of the very normal rules of computation that we're used to from integers also in this modulo world. And if we have all these properties, we call the system we're looking at, or the data type we're looking at, a group in mathematics. So a group means we have a set of values that our variables can take. So that's the Zn here, where Z is the symbol for the integers, and the subscript n means we're computing modulo n. So with representatives 0 to n minus 1. So we need a set for a group and an operation. Let's have a look at the addition operation first. So addition modulo n could be implemented as you just add the two input numbers as integers, and afterwards you apply modulo n. If you do that, you also get a number between 0 and n minus 1 again. And this computation has some of the nice properties that we know. Like, for example, if we're adding 3 numbers, it doesn't matter whether we first add the latter 2 and then the result with the third one, or first the first 2 and then the result with the third one. This looks pretty obvious, but it doesn't hold everywhere. It does hold in our modular arithmetic. Addition is also still commutative, so you can swap the order of operands. And we have some magic elements. We have one very magic element, which is called the neutral element, which is neutral, which means if you combine any other element with it, so add this neutral element 0 to it, nothing actually changes. Okay, and then for each element in our group, we also have a so-called inverse element, which sort of undoes the effect that the element itself had. So for example, if you want to undo the effect of plus a, you do, well, minus a. Looks pretty obvious, but it's still very convenient to have. So the additive inverse of any element is minus that element. For example, modulo 11, the inverse of 1, let's have a look at the table. So this is an addition table which says first operand, second operand, and here the result, what we get for the computation. So for example, 3 plus 7, which is 10, is also 10 modulo 11. But as soon as we have a result that would be bigger than 11, or at least as large, for example 3 plus 8, we would get 11, but 11 is represented by 0, so the result is 0 again. And we can also see that in each line there is one operand which leaves it unchanged. So for example, 3 plus 0 is 3, and so on. And we have these inverse elements such that if you add them up, you get the neutral element, which has no effect, so to say. So for example, the additive inverse of 3, let's have a look, that's 8, because 3 plus 8 is 0. Okay, so adding is nice and all, but it's not really satisfactory. So we would want a bit more. And in particular, we also want to multiply. And actually multiplication is quite a bit more interesting. So unfortunately, by itself, multiplication modulo n does not give us a group. And the reason for that is that not all elements have an inverse. So for example, if we look at modulo 11 again, we would want to satisfy these same rules here. We have a neutral element which is 1 for multiplication, because multiplying by 1 doesn't change anything. But we don't have an inverse element for every element. What this would mean is that for each number we would need to find a second number such that number A times number B equals 1. But that's not possible for all numbers. For example, for 0 we can't find any number, any inverse. We cannot find any number such that B times 0 equals 1. It's not possible. So that's why we don't have a group. And this means we need to modify our set a little bit. So we need to kick out all the numbers that don't have an inverse. Then what we have left is a group. So that's why we define a set that we denote by Zn, like before, but with a little asterisk on top. So we call it Zn star. The Zn star is simply the set of all elements that we already have modulo n, but we kick out all the numbers that don't have an inverse. And then this slightly smaller set is actually a group. So again, here we have an example X multiplication table, modulo 11 with multiplication. So we see, for example, 1 times anything is whatever was the second input. That's easy. Let's have a look at this row here. So 2 times everything. So that's easy so far. 2 times 5 is 10, as everybody knows. 2 times 6 would be 12, but 12 modulo 11 is 1. Okay, so this also means that 6 is the multiplicative inverse of 2, because the result is going to be 1. So we see that the inverse of numbers here has nothing to do with the fractions or comma numbers or anything, but it's just whichever entry gives us a 1 in this lookup table here. Okay, one question you might ask is, how big is this set? How many numbers are in there? And to answer that, we need a few more math terms. And the first term is the term coprime. So when are two numbers coprime? You know when a number is prime, so a Primzahl, it's prime when it doesn't have any divisors except itself and 1. Or it has exactly two divisors, itself and 1. That's a clearer definition. So when are two numbers coprime? They are when they have no common prime factor. So for example, the numbers 3 and 5 are coprime because there is no prime number that divides both 3 and 5. So why is this term useful? It's useful because with this coprime property, we can test whether an element has a multiplicative inverse. So a number A has such a multiplicative inverse modulo n if and only if the two numbers are coprime. So if the modulus and the number we are trying to invert have no common prime factor. And if that's the case, then we can find this inverse, well, either by setting up the full table, but that's often very inconvenient, or with an algorithm. And one of the algorithms that some of you might know is the extended Euclidean algorithm, which is really just a simple computation rule that sets up a little table, and at the end of the table you get exactly the inverse of the two. I'm not going into details here, but if you're interested, you can look it up easily on Wikipedia or so. There's a good explanation. And it's really very simple to evaluate. Okay, so that gives us a criterion when a number has a multiplicative inverse. And of course, that also means it tells us something about how many numbers are in the set. But to be a bit more precise and to give a name to this number, to this size of the multiplicative set, we actually have a function that does that. This function is called the Euler phi function, denoted by this little phi of n. And if the input is n, then the output of this function is the number of integers in the range of 1 to n minus 1, which are coprime to n. So in other words, that's the number of numbers which are invertible modulo n. So how big is this number? Let's have a look at some examples. If p is a prime number, then which numbers below it are coprime to p? Well, can there be any number smaller than p which has a shared prime factor with p? No. Of course not, because otherwise, if it would have such a shared prime factor, it wouldn't be prime itself, right? So that means that all numbers less than p must be coprime to p, except 0, because the prime number that divides both 0 and p is p itself. That's why 0 is not in the list here. But that means that the Euler phi function of any prime number would give out p minus 1 as a result. So that means if we are computing modulo a prime number, all other numbers in the set except 0 must be invertible. That's great. What if we look at a composite number? For example, at a number with two prime factors, p and q. Well, which numbers less than p times q don't have a shared prime factor with p times q? Well, the only prime factors that could be interesting here are p and q, because these are prime numbers. This means that all multiples of p and all multiples of q below p times q would have a shared prime factor. So we need to take all numbers pq minus 1 and then subtract all the number of multiples of p, which is q minus 1, and the number of multiples of q, which is p minus 1, to essentially get the result. So this was maybe a bit hard to follow, but the final result is very easy to remember. Phi of p times q is simply p minus 1 times q minus 1. So let's have a look at a number example, namely at the number 15. 15, as you probably know, but as is very difficult to find out, for example, for quantum computers, is 3 times 5. So that means phi of 15 must be 3 minus 1 times 5 minus 1, which is 8. And we can also list these 8 numbers here. So the coprime numbers to 15 are 1, 2, 4, 7, 8, blah, blah, blah. And you will notice that the missing numbers are exactly the multiples of 3, like 3 and 6 and 9, and the multiples of 5, like 5 and 10. Okay, so this function is going to be quite useful for the encryption system, but we need one more concept before we are done. And this is also actually linked with the phi function. And this is the context of generators. Because if we now look at this set of invertible elements in our group, then we might wonder whether we can describe them in some way or whether we can generate them in some way. And in fact, we can. So let's have a look at generators. So we saw already that the size of this set is actually determined by this phi function here, because every coprime number is invertible. And we only keep the invertible numbers and kick out all others. Now the interesting thing is that this phi function also appears in a very handy equation. Namely, if we're looking at multiplication, we can of course also multiply any element a with itself as often as we like. So we can, in other words, exponentiate it. So for example, a to the power of 3 would be a times a times a. And if we do this very often, so multiply a by itself very often, namely 5n times, then this little theorem, Euler's theorem, tells us that the result is guaranteed to be 1 modulo n. Why is this interesting? Why do we care about exponentiation giving us a 1? The reason why we care about this becomes apparent when we look at what happens next. So a to the power of phi of n equals 1. Okay. What does that mean for a to the power of phi of n plus 1? So multiplying a one more times. Well, then the right hand side must be 1 times a, which is a. But a has already appeared in this sequence, right? It must have appeared right at the beginning, because a to the power of 1 was also a. Interesting. What happens if we do it again? So if we multiply the result, so this equation by a and a again, so by a squared, then we again also get a squared at the right hand side, because the a to the power of phi of n, which is 1, simply sort of can be cancelled out, because it results in the neutral element. So this means that if we look at the powers of a number, like a squared, a to the power of 3, and so on, this starts repeating after a certain time, and in particular it repeats after phi of n values. So this means we can ignore the effect of any larger exponent and can simply reduce the computation to a computation with an exponent smaller than phi of n. If you found this verbal explanation a bit hard to follow, let's have a look at an example. And let's look at in particular one more interesting number. So I said that after a while things start repeating. They definitely repeat after phi of n multiplications, but they might also repeat at an earlier time. So there are some numbers where you don't need to multiply phi of n many times before you get a 1, but a smaller number might repeat. One such example number is if we choose a equals 1. So we only certainly need to take 1 to the power of 1 before we get a 1 as a result. That's very easy to see. So there are numbers which have already a smaller order t, so t is called the order. But we are particularly interested in the numbers which have a large order. So where there is really no t smaller than phi of n with this property. So there is no period, no repetition point smaller than phi of n. These are the interesting numbers. This is because when you look at all the powers, they must generate phi of n different values on the way here. And all of these different values are actually all elements in the set Zn. So this means a number which has this property that its order is phi of n can actually generate all other numbers in the set. So that's great, and that's why we call them a generator. So as an example, if we're looking modulo 11 again, and at the set Z11 star, which includes all numbers except for the 0, because 11 is a prime number. Then one of the generators of this group is 2. Let's have a look at why that is. So let's look at the powers of 2. 2 to the power of 1 is 2. That's very easy. So let's start counting there. 2 to the power of 2 is obviously 4. Okay, so we can generate 4 from 2. We can also generate 8. But now it becomes interesting. So 2 to the power of 4 would be 16, but modulo n, 16 is equivalent to 5. So next we jump to the 5 here. And so on and so on. So whenever necessary we reduce, and we see already that we jump from one point to the next and we never have any repetitions. And actually we don't have any repetitions until we reach phi of n. Phi of 11 is 10. Which would give us, based on the previous computation, 12, but after reduction it gives us 1. So now we see here, if we follow this track, we've generated all the numbers in the set. If we would go any further, like 2 to the power 11, we would get 2 again, and we would start repeating. Okay, so this is why 2 is a generator. Its powers generate all numbers in the set. So why is this kind of number interesting? That's because this capability of 2 also gives us an interesting question to answer. Because if 2 can generate any value in the set, we might wonder, how long does it take to get there? So now, how long does it take for 2 to generate, for example, 5? And this problem is called the discrete logarithm problem. And I see that there is a question, so let's have a look at that first. How do you find such generators is the question. That's actually a pretty tough one, because finding them is not easy. So in particular, it's too difficult for me to actually explain here, but there are some algorithms that can both test for this property or generate a number accordingly, but it's definitely beyond the scope of this lecture here. So sorry, no answer to that one. But it's definitely something that we need to do very often, and in particular we'll meet an algorithm in a moment where we need such a generator. And the good thing is that if you think about cryptography and you want to use this kind of problem, then there are usually predefined groups and predefined generators that you should use. So that's why you never actually need to worry about generating generators, because you already get them. So there are standardized generators for different security levels, for example. Okay, so let's have a look at that problem. So SAD, not SAD, but SAID. And that's the discrete logarithm problem. So what's it about? It's about exactly what I just said, namely, if you have a prime number, your modulus, and you have given a generator of this group, so of the set ZP star, and you have a challenge element Y. That's the element you want to reach. Then the problem or the question is, what exponent do you need to use? So how often do you need to multiply G by itself in order to get the challenge element Y? So going back to the previous slide, we might be asking, what exponent do I need for 2 in order to generate, for example, the number 5 here? And the answer to that question in that case would be 4. So for this reason, we call 4 the discrete logarithm of 5 with base 2. That's the terminology. Okay, so why is this problem interesting? Oh, at least the cats find it interesting. It's interesting because it's believed to actually be pretty hard if we look at groups modulo a large prime number. Oh, don't you like prime numbers? No. You like food, huh? You'll get food in the break. We're going to get to the break in a moment. Okay, so this is believed to be a very hard problem. So in a similar way that, for example, NP hard problems are believed to actually be hard. Okay, so that's the problem. Here is again an example. So on the slide, it's actually the example with the challenge number 10 instead of 5. But we can still have a look at what the answer is. So we could to solve this problem, for example, try all possible exponents until we reach our challenge number. So let's see, blah, blah, blah. We know that after 4 steps, we already reached the 5. Still not the right answer, but very close, because one more step and we would actually reach the 10. So again, this means that the discrete modulus of 10 to base 2 equals 5. So 5 is the discrete logarithm. Why is it called discrete logarithm? Well, it's the logarithm because you're trying to find the exponent. That's what logarithms are about. And it's called discrete because we're only talking about integers. Okay, so this is one of the interesting problems that we're going to use for our crypto systems. There is one other problem, and that's the so-called integer factorization problem. So this is a bit easier to explain because it simply states you're given a number n, any integer or natural number, and you're supposed to find all the prime numbers that this number is composed of, so all its prime factors and the corresponding exponents. This is a problem that can be easy to solve in some cases, like for example, if n is a power of 2 or so, even if it's very large, you could relatively easily find that it's only composed of 2's. But there are cases where this problem is pretty hard. And the hardest cases are where n is the product of only 2 prime numbers. So n equals p times q. And in that case, the challenge would be find p and q. So as an example, if you're given as an input the number 143, you would have to find the factors 11 and 13. And these two problems are two of the most important ones when it comes to asymmetric cryptography. So all of the classical, or many of the classical asymmetric crypto systems, and definitely the most widely used ones, are based on these two problems as their primitive. There are also a few other problems that we can use, and in particular we also often want to do that because these two problems, while they appear to be hard on classical computers, don't look so hard on quantum computers. So for this reason, more recently there has also been quite a lot of research about alternative problems where we don't have a clue how we could use quantum computers to speed things up. Okay, we have a question. Let's see if I have a reasonably empty slide to show it. Well, not really. Let's try this one here. Let's see. Okay, it's a cat question whether I painted the cat black. I have 2 cats, and one of them is black and white, and one of them is black and white and red. Okay, but he does look like painted occasionally. There is another suggestion about what might be the reason. It's still in color, it's just encrypted in ECB mode with a constant nonce. Very sneaky. Okay, well, it's not painted, it's just usually too shy to show up. That's why you all mostly only know Hexe and not Wichtjet. But he's lovely. Okay, let's close the questions and go back to what we're trying to do. So let's have a very brief look at our first crypto scheme that we want to build. And right after this short look, and before actually explaining how it works, we are going to head into a short break. If you have any preferences for how long the break should be, now would be a very good point to drop this information in the chat. Okay, so let's have a look at the first target scheme, namely key exchange schemes. So what's the point of key exchange schemes? Just repeat, the point is to establish a secure communication by having 2 parties agree on a symmetric key that they can use afterwards together with a symmetric crypto system. And this key exchange scheme was actually one of the first proposals that were made regarding asymmetric cryptography. So this is really a relatively new field compared to the rest of cryptology. So people have already been doing cryptology since ancient times. So we know crypto systems from ancient Greece, from ancient Rome, and so on. But all of this was usually symmetric. And there was also a good reason why that worked out, because much of it was in a military context, so people always knew each other beforehand. But in the 1970s, there was a bit of a small revolution, I would say. And that is that normal people started getting access or getting a need for cryptography. Because the 70s is when some first public systems over different kind of networks or over a distance started appearing. Like, for example, in the TV context or also in the banking context, it started to become relevant for normal people to encrypt stuff, or at least they noticed it. And this is why this is the decade where two things happened. The first thing that happened is that we started having public cryptographic standards. So crypto systems with publicly available, well-documented specifications. In particular, that's the decade when the DES was standardized. And the second thing that happened is that people started thinking about using cryptography in contexts where you don't already know each other in advance, where you can't just pre-distribute all the key material. And that's why in the 70s we got our first key exchange scheme, the so-called Diffie-hellman key exchange, named after the two inventors, Whitfield Diffie and Martin Hellman. So they proposed the first asymmetric crypto system. You also sometimes find the name Diffie-hellman and Merkle for it, because Merkle was the guy who came up with the concept of asymmetric cryptography. So that's him. You might recall his name because he actually also worked on hash functions. So we talked about the Merkle-Darmstadt constructions. And that actually arose also in the context of an asymmetric scheme. So this was a really massively impactful invention at the time, so in the 70s. And this is also why this invention has been awarded the Turing Award a couple of years ago. So what's it about? It's about solving this key distribution problem. And that's why it often, very often in today's protocols, makes the first of two steps, namely the step where you set up your key material. So this is the phase where in many protocols today you use asymmetric cryptography, and then for the actual communication afterwards you use symmetric cryptography. So these are the two main parts, and this is the first real solution to this first challenge here. Okay, and with that I would suggest we head into a break. Let's have a look if we got any suggestions on the duration. So somebody requested to have a full 15-minute break after all the math we talked about. That's fine from my perspective. Somebody else is asking for 10 minutes. So I would suggest the trade-off. Let's do a 14-minute break and let's reconvene at 11 sharp. Okay, so have a nice break, relax your brain, get a coffee or some breakfast, and see you again at 11. In the meantime, enjoy your break.
Deswegen mein Frosch. Digga, hast du Hunger? Es tut mir so, als hättest du jetzt gerade Leckerlis bekommen, ne?
So here we are again. Welcome back from the break. And I see in the meantime we've used the time for some questions. Let's have a look at that. So the first question is looking at the concept of generators again. So somebody is wondering whether you can also use other mathematical functions so other than the exponent, to create generators. Well, yes, you can. In fact, generator is a concept which you can try to apply in any group which has approximately the structure that we're looking at here. So in particular, you could also talk about an additive generator. What we've looked at is the multiplicative generator. So you multiply the generator by itself to generate numbers. You can also look at the additive generators, where you add a number to itself. But it turns out that additive generators are a lot more boring than multiplicative generators. So for example, or at least if you're talking about integer arithmetic. So for example, if we look at addition modulo 11 and we look at the generator 1, can 1 generate all other functions? Well, yes, because 1 plus 1 plus 1, however many times, definitely generates all other numbers. But finding out the secret here, so the discrete logarithm, which in this case is just a division, is trivially simple. So not all groups and generators actually lead to a sensible crypto system. But there is one other construction that we do know that is really, really useful for cryptography, where we have a different kind of operation which we call addition, but it doesn't work at all like the integer addition that we know. And this other kind of group where addition does give a useful function for having a generator, this is called the elliptic curve group that we're talking about. So that's one other way that has some advantages over the multiplicative group here. I have some short notes on that. I don't know, either later today or next week. I'm actually not sure where it is in the slides. I think it's next week. There I can give some more comments on that. Okay, so yes, there are other functions. Somebody is confused as to why the key exchange is considered asymmetric, because it seems similar to symmetric crypto. That's actually a good observation. So I do agree that the concept of asymmetry is not immediately visible here. But we will see in a moment that what actually happens in most key exchange schemes is that you have not just one key pair, but two key pairs, but each of them is asymmetric. So it's like you set up a public key encryption in one direction and in the other direction. So two people do talk to each other, but each of them has a part of a secret that they don't share because they can't, they have no means of sharing it. So each of the participants does have a secret that only they know and that only they can use, but they publish some information and they exchange that with each other. And that's why if you just look at the picture of it, it sort of looks symmetric because both people are doing similar things, but they each have their own secret that they don't share. That's what makes it asymmetric. And we will also use the term of public and private key there, so then it will hopefully make more sense. Yeah, but thanks for being skeptical of the things that I claim. So I think it helps understanding. Okay, let's look back, and in particular, since we've just had the break and the break was really long, let's have a brief look at what you actually remember from before. So the question is, what's a new word or concept that you've learned so far? I just need to gain focus again so that I can go to the next slide. Okay, so give me your whatever you remember from before the break. Okay, so I'm glad there are a few things that you do remember. So, let's ignore the parts that have nothing to do with the lecture. So what some people remember is different crypto systems, like the discrete logarithm and PGP and key exchange, so different contexts. We have some off-topic things like different cats, okay, also fine. Co-prime was a really important concept of two numbers not sharing a prime factor. Apparently some people stuck in your memory. That's also nice because they were very influential and did a lot to advance the field. What else do we have beside several mentions of another professor? We have some things that actually refer to last week's content but still popped up only today. Substitution permutation networks. Okay. Those are actually two different things, I would say, because I didn't talk about Euler primes, but I did talk about Euler's theorem and the Euler phi function and prime numbers on the other hand. Maybe you can remember a few more keywords from the discrete log context. So maybe you can come up with some terms, how we call the individual parts in there, or maybe something more on modular arithmetic. Let's see, what do we have here? Generators, that's a very important concept, which we need again in just a minute when we've finished with this. Let's see if there are one or two more inputs. Maybe you also remember a second problem, because I'm only seeing the discrete logarithm problem here, but we did have a second hard problem. Maybe you can recall what that was. Well, maybe the break was a tiny bit too long if so much of that has disappeared. But the good thing is, of course, you can rewatch it at a later point in case it's necessary. Okay, so some more things did appear. Let me search for them. Where are they? I actually don't find the new one. I just saw that it changed. Well, okay, let's leave it at that if not much more is incoming. And let's have a look at the first actual scheme that uses all the math that we've looked at before the break. So this scheme is called the Diffie-hellman key exchange. We already know that, but how does it work and what does it need? So the first important thing to know is that for the whole thing to work, you actually need some public system parameters. So these are some parameters you agree on beforehand. So that's like in symmetric cryptography, we agreed on the cipher beforehand. We agreed to use, for example, AES CCM or so. And here you also need to agree on some things, but they are much more specific. So in particular, you need to agree not just on using Diffie-hellman with a particular key size, but you need to agree on an actual prime number and a generator. But all of this is public information, and in particular, it can also be the same system setup for a lot of different people talking. So it's not anything that's specific for your particular communication, but for example, there is a standard by NIST which says, okay, if you want 128-bit security and this flavor of Diffie-hellman, then use this prime and this generator, hard-coded, very long strings. Okay, so these are our system parameters. And the generator should be a generator of the multiplicative group modulo p. So what do the two people do? Remember, they don't have any shared information beforehand. They only know the system parameters. So what do they both do? It looks very similar, but let's first look at Alice's perspective. So first step that Alice does is she comes up with a random number. So this must be securely randomly chosen in this range here. So essentially it's a number smaller than p, but there are some numbers like +1 and -1 that aren't so suitable. And she chooses this random number, and this is going to be her private key. She never gives it away. What she does give away is a function of this number, namely the exponentiation function. So she takes the public generator and raises it to the power of her secret exponent, modulo p. And she sends the result of this computation, but not the input, to Bob. Bob does essentially the same thing, so he also chooses a securely random number in this range, also takes the generator to the power of this exponent and sends it to Alice. So they both have sent each other a function of their secret, but not the secret. But the nice thing is that using the rules of the computation rules of exponentiation, they can now both derive the same value k. So k is going to be their shared secret key afterwards. And what they do is they take the number that they received and raise it to the power of their own secret private key, modulo p. So you see the computations look slightly different. The one is a to the power of b to the power of a, and the other one is alpha to the power of a, and then to the power of b. Because it's based on what they got from the other person and their own secret. But the result of the two is the same. Why is that? Well, let's have a look at it. If we know computation rules, then alpha to the b to the a is the same as alpha to the b times a. So in braces, that's what's written here. So these two are equivalent according to the normal exponentiation rules. You can, of course, change the order of multiplication here, because this is commutative. And then this is again by the same exponentiation rules, the same as alpha to the power of a and then to the power of b. So you see that the two values that they derived are actually the same, even if they went a different way to get there, but they both got the same number. And they can now use this number as a basis for a secret key. They might not use it directly, so for example, they might first put this number into a hash function or something to get a value of the right size, because they're typically going to operate with numbers that are a lot bigger than symmetric keys. We're going to see that in a moment. So they might do some post-processing to this, but essentially that's it. That's going to be their shared secret key. Now the big question is, why would this be secure? Why can someone who observes all of these messages, not get the same key? So how does it work that they two get the key, but nobody else who knows the messages and thus knows a function of A and a function of B does not? But before we look at that, I think we best have a look at a number example. So let's again recall our example of computation modulo 11. So in Z11 star. And let's again pick our favorite generator 2. So these are our public parameters. Now Alice throws her dice and chooses a value between 2 and 9, which results in 3, and sends to Bob the result of 2 to the power of 3, which is 8. Bob does the same thing. Turns out that this time he chooses randomly the number 5. We remember that 2 to the power of 5 modulo 11 was 10, so that 10 is the value that he sends to Alice. Now Alice can derive the key by taking the number 10 that she got, raising it to the power of her own secret exponent, which is 1000, and after you do the reduction, turns out the result is 10. Okay, Bob does the same thing, so he receives a different number, raises it to his own secret number, gets a totally different looking result, but modulo 11, it's actually the same. Okay, so this is the magic part, that they both get the same value, and the other magic part is that nobody who sees 8 and 10 can actually recover this value 10 that is the secret key. So let's have a look at what hard problem this is based on and what everybody knows. So again, Alice and Bob have no shared secrets beforehand, and the adversary, Eve, knows all the exchange information. So she knows the public system parameters, the prime number and the generator. She knows Alice's public key, alpha to the A, and Bob's public key, alpha to the B. And what you would like to derive from that is alpha to the power of A times B. And this question that Alice faces, how to get this from that here, this is the so-called Diffie-hellman problem. And it turns out that we don't know exactly how difficult it is, but the best way we know of solving it is to apply a discrete logarithm algorithm to one of these two numbers here. Because if Eve is capable of computing discrete logarithms, she could recover the private key from the public key. And if she could do that, then she could repeat the computations of either Alice or Bob. So what we need to do is we need to choose the prime and the generator and their bit size in such a way that solving discrete logarithms modulo p is impossible for Eve, is not feasible. And for this we need a certain key size. So in other words, we need the numbers involved to be large enough such that recovering the discrete log is too difficult. Now, how difficult is it? We already saw one way of recovering a discrete log earlier when we looked at the number example. So we could simply try to brute force it. We could try all possible exponents b until we find one that produces the observed result of alpha to the b. That's one way of going about it, but it's very slow. And it turns out that we do know some better algorithms. So the runtime of this brute force algorithm is actually exponential in the bit size of the modulus p, right? Because if p, for example, is a 128-bit number, then we would have 2 to the 128 possible numbers below that approximately, and the number of possible exponents is also approximately that, a tiny bit less, but approximately that. So the number of possible options to go through would be exponential. But it turns out that we actually do know some sub-exponential algorithms of solving this problem. So they're a bit faster than exponential, but they are not polynomial in runtime. So there's a class between the two actually, which is super polynomial but sub-exponential. And this is the class that we believe these problems belong to. And this is why we need to choose a key size here that is a lot larger than the security bit level. So in symmetric crypto, if we want 128-bit security, we would choose a 128-bit key. Here, we need a much bigger key. And in particular, for 128-bit security, the recommended bit size for the prime number is over 3,000 bits. The recommendation varies a bit, so some people will tell you 4,000 bits, some will tell you 3,000. Both should, according to current knowledge, correspond to a 128-bit security level against classical adversary, so without quantum computers. And the reason why this number is so much bigger than 128 is because of these sub-exponential algorithms. Okay, so this is a bit inconvenient because it means we need to do all our computations using very, very big numbers. So this is going to be very expensive. And that's actually a general property that the known asymmetric schemes that we have, namely that they are a lot slower to execute than symmetric crypto. Because they often need very big numbers, they need to do complicated operations like exponentiation, which we're going to take a more detailed look at later, and all of that makes them pretty slow. Okay, so that's what I wanted to say about the key exchange. Let's first have a look at the question related to that just appeared. So let's get back to a reasonably empty slide. I'm afraid I have none. This one here. Okay, let's show the question. So the question is it possible to intercept the randomly chosen number? So I guess this refers to this picture here. Is it possible to intercept this randomly chosen number? Well, hopefully not, because if an attacker manages to somehow get access to this random number here, then they have broken the scheme, because then they know Alice's secret and can generate the result of the computation using this secret and the publicly known value that's sent from Bob. So if the attacker gets access to this number, for example, because Alice uses a weak random number generator and the attacker can predict the result, this would be fatal for the scheme. So it's really important to have a good number generator here, and that's actually not so easy because you remember these numbers are very big, so you need to generate a very large number in this range. So that's quite a bit of effort, in particular if you think of some weak or small devices which maybe don't have a good hardware random number generator. This is actually rather difficult. But this key should never leave Alice's computation device. So it's of course needed on her machine so that she can complete this process here. but it should never leave that machine. It should never be sent anywhere. It should never be stored anywhere in an unprotected way, because it's the secret key. In practice, if you store your secret keys or your private keys for some asymmetric crypto system on your hard drive, these are usually protected, for example, by a password and by limiting the access rights to the file. So these are two of the measures that you usually take when storing a key, because you might have to store the key somewhere, just like you might have to store a symmetric key somewhere if it's a long-term key. If it's a short-term key, you don't need to store them long. So for example, if you complete this protocol once and have obtained the shared secret key, you can actually throw away your secrets afterwards, because you need them only for this one computation here, and afterwards you can use this one for however long the communication session takes. And when the communication session is over, you can also throw away this key, and next time you can start from scratch with fresh random numbers and fresh session keys. That's what's usually done. Because we don't want to have to store the keys, and because there are some additional security benefits of changing your keys regularly. Another question appeared in the meantime. So I should repeat why the key has to be so long. In the short answer to this, but it's maybe a bit incomprehensible, so the short answer is because we have some algorithms that can find the discrete logarithm faster than brute force. Brute force would be what we've seen on one of the previous slides. So let's see, this one here, this was a brute force search, right? So we tried the possible exponents one by one, and the number of tries that we would need is exponential in the bit size of the modulus, because there are 2 to the bit size many options essentially. So that's brute force. If this were the fastest algorithm, it would be okay to use a 128-bit key. But unfortunately, there are faster algorithms. One of them is actually related to the birthday paradox. So we can do a trick that is related to collision finding to find the discrete log. If you're curious how that works, my recommendation would be to watch the corresponding lecture in the cryptography course, which is called discrete logarithm, I think. So that would already double the required bit size. But it turns out that there are even faster algorithms than that. And this is, for example, using the so-called index calculus methods. And the same thing actually also holds for the factoring problem. So there are also factoring algorithms which are faster than exponential runtime. So the runtime doesn't look like some constant to the power of n, where n is the bit size, but it looks like something smaller than that. However, it's also bigger than polynomial, so it also doesn't look like n to the power of some constant, but it's something in between. There's actually a very special kind of notation for how to write these functions which are more than polynomial but less than exponential. And this is the runtime of the fastest algorithms we have. So that means that the time for cracking a 128-bit key is a lot less than 2 to the 128. Maybe it's something like, I don't know, that's a random number now, something like 2 to the 40 or so. I haven't computed it, so that's really just a guess. And that also means that a larger key, like for example, 1000-bit modulus, so the discrete log problem modulo a 1000-bit modulus, would take something like 2 to the 80 operations, which is 80-bit security. And in the 3000 bits we're looking at here, the best algorithms that we know have an expected runtime of about 2 to the 128 plus a bit, so a bit larger than 2 to the 128. And that means that we say that solving the problem has 128-bit security, because that's the expected runtime of the fastest algorithm to break it, to recover the private key. And because this is now the smallest, so this is the bit size that corresponds approximately to the runtime we want to have, we choose this bit size as the bit size of the modulus. Next question is about the Diffie-hellman key exchange. It needs to be done with integrity and authenticity, otherwise an attacker could send a custom alpha to the A. Wow, that's a very good observation, and it's absolutely correct. So let's have a look at the picture. So the question is about what Eve can do. In my explanation, I have assumed that Eve can only see these two messages and tries to recover the secret from that. But it's totally correct that a very powerful attacker could actually do more. So Eve could try to sit here in the middle, would get the message from Alice, and would forward a secret message based on her own private key to Bob. Bob would answer. Eve would see that, notice the result, so she would now have a shared key with Bob. And then she could send a result based on her own secret key back to Alice. So then Eve would sit in the middle, this is called a person in the middle attack, and have a key with both of them, and both would believe they are talking to each other, which they actually aren't. So that's a dangerous attack, and that's why when you do this scheme, Alice and Bob also need to ensure each other's identity first. But we're going to look at that in next week's lecture when we look at the structure of a protocol. And there we will see that exactly what you suggest happens, namely that we additionally protect the integrity and authenticity of these messages here. Okay, what else do we have here? So somebody is thankful for the explanation. You're welcome. And what's the difference between brute force and exhaustive key search? That's the same thing in my opinion. So both of them mean we try all possible options. So in AES, for example, brute forcing and exhaustive key search would both mean I try all 2 to the 128-bit possible keys until I find one that works. Where works usually means, for example, it matches with one known plaintext ciphertext pair that I have. Or in the Diffie-hellman key exchange, brute force would mean I try all possible exponents until I find one that produces the observed public key. We use both terms interchangeably usually. So then, solving a DLP will not be secure with quantum computers. How would you make a safe principle of this key exchange even work? Yes, indeed. So quantum computers are a threat for this kind of problem. And that's why we are researching different hard problems. The downside is that these different hard problems haven't been researched for as long as the Diffie-hellman problem, for example. So the amount of trust we have in them is maybe a tiny bit less than we have in the current problems. That's why I'm still explaining the current ones. The other reason why I'm still explaining the current ones is those are the ones you see everywhere. Those are the ones you can choose in the protocols. And they're also, in fact, a lot easier to explain. So some of the other hard problems which are not susceptible to quantum computers are, for example, related to lattices or to error correcting codes. And that would make the first half of this lecture, where I explain the math background, a lot longer. So that's why we're focusing on these well-known and currently widely used ones. The reason is, or the issue is, that we also don't have a standard yet of something that will be post-quantum secure. So I wouldn't even know which scheme to pick. We currently have a competition looking for them, but we don't have the outcome yet. So now whenever you build up a connection, you will essentially always see Diffie-hellman as the algorithm that is used. Okay, back to the slides. So we've already jumped through this part here. And we are now ready to have a look at the second problem, or the second challenge that we want to solve, besides key exchange. So the key exchange we've seen so far requires both parties to be online at the same time in order to be able to exchange their messages properly. What we would really like to have is a scheme where I can just send a message in one direction. The recipient will be able to read it, but nobody else will. Which is useful, for example, if I want to send somebody an encrypted email where I can't do this key exchange protocol properly, or at least not easily. Dear camera, here I am. Please focus again. Let's see. It's very reluctant now. Okay, here we are back. Okay, so asymmetric encryption, how does it work? So what kind of interface are we talking about? We often call the interface we are talking about here a so-called trapdoor one-way function. Let me first explain what we see here, and then I explain why we call it a trapdoor one-way function. So what we see here is a very good comparison to what an asymmetric crypto system works like. So we want something, a mechanism, that is easy to lock. For example, in our case, this would mean easy to encrypt. Like a regular lock that like the physical thing. Easy to lock, you don't need anything for that. However, it's very hard to open. In our context, this would mean it's very hard to decrypt, so to compute the function backwards, unless you have an extra bit of information. In the real physical thing, this extra information is the key, and in our case, this information is also the key, the private key. So for locking, you don't need much, you need only publicly available stuff. For unlocking, so for decrypting, you need something, and that is the key. So in other words, we want something that looks like a one-way function if you don't have the key. One-way function means it's easy to compute, but it's hard to undo, to compute backwards. So to compute the inverse function, you can only go one way in the function easily, the other way is hard. Unless you have a piece of trapdoor information, and this trapdoor information is the key. And this allows you to actually go backwards, so to do this reverse step. So I don't know if you have psychic powers, the people who are calling for cats here, but the cat actually did just enter the room, but she went to her sleeping place, so we won't see her, unfortunately. Okay, so let's match this three-part story into actual algorithms. And we're actually going to start by looking at this key part first. So what's the point of this key thing, and how do we generate it? What's the algorithm connected to it? We call it the key generation algorithm. Very creative. What does it do? It actually generates not just one key, but two keys. A private key and a corresponding public key, which matches for a particular private key. This is done by the owner of the key pair. This owner is Alice in our example. So she has these two keys. One of them she can distribute publicly. So for example, she might upload them to a key pool in the case of the PGP email system. Or she might, for example, put it into a certificate and publish the certificate on the website. So she makes it available and she tries to show people that this is her public key, convince them in some way. The other half, the private key, she keeps safely to herself. So for example, she stores it in a key, password protected, and what have you. Okay, so that's the key generation part, two keys. Notice one terminology thing. So I usually call the key she keeps secret here a private key, because it's only privately for one person. In symmetric cryptography, we also have these secret keys, but there I call them secret, because they are shared secret key between two people. Private is just for one person, secret is between two people. Okay? So what can we do with these keys? One of the things we can do is the locking part, and that's the encryption. And for this we only need the public key, which means anybody who has access to this key, which is essentially everybody, can encrypt a message with it. So this looks a bit or sounds a bit like the symmetric scheme, except that you need the public key and not the secret key for it. But still you map a message to a ciphertext, and you send the ciphertext to Alice. Alice, who has the private key, can now take the ciphertext and decrypt it to get back the message. And she does that with the decryption algorithm that requires the private key. Only she can do it, nobody else. And so even somebody who sees this ciphertext transmitted over an insecure channel and who knows the public key still cannot combine this information to get back the message. Only Alice can do that. Again, the story of these schemes started in the 70s, and at the time, three cryptographers or mathematicians, or both, Ron Rivest, Adi Shamir, and Leonard Edelman, came up with the idea for the RSA encryption scheme, named after these people. And they also received the Turing Award for it, just like we heard about earlier with the key exchange scheme. So, what does this algorithm do, and how do what do the three partial algorithms look like? Key generation, encryption, and decryption. Let's first look at the key generation, which is by far the most complicated part actually. And to understand these definitions, please keep in mind this cheat sheet here, which summarizes some things we've heard before the break, right? Before the break, we talked about this phi function here, which gives the number of invertible elements, modulus and modulus. And we also talked about co-prime numbers and this magic Euler theorem, which tells us that any value to the power of this Euler function on top here equals 1 modulo n. So if we put n into the Euler function, of course. So these are the ingredients we need here. And what are we going to do for the key? Since this is related to the factoring problem, we are going to first define a difficult factoring problem. A difficult factoring problem consists of a number which is the product of two primes. So the first step in key generation, we choose these two primes, p and q. This is now very different to the primes we saw before. Before we said that the prime could be public in Diffie-hellman. Here, the primes are a big secret. So everybody who wants to work with RSA and generates the private key needs to find their own random primes and must keep them a secret. So, and they must also be very large. So this is again actually very difficult to implement, and this also in practice very often went wrong in the past because of not using proper randomness generation, or because there are actually a number of mathematical properties that the prime numbers shouldn't have if they are supposed to be secure. So this is actually a really challenging way of generating keys, having to generate two secure large primes. It's a lot harder than, for example, in the AES, where you just need to come up with any 128-bit string. That's it, as long as it's uniformly random. So here this is more advanced. And if we have those two prime numbers, we multiply them together to get a modulus. And this modulus is supposed to be hard to factor afterwards. So that's the preparation step. And now for the actual key, we have a public and a private part. And both of them are going to be exponents. So the first exponent, we can just choose however we like. It doesn't need to be random. It can actually be something like 3 or 16,000 and something, which are both often used values. That's not so security critical. It only needs to satisfy one thing. It needs to be co-prime to phi of n, of this modulus n here. That's the only criterion. If we have this public exponent, then we can derive the private exponent from it. But of course, not just by using only the public part, that would be critical. We could derive the entire private key from the public key, that would be really bad. So we need an extra piece of information. And this extra piece of information is the value of phi of n. Why is this value secret if the modulus is public? That's because if we look at the definition of the Euler function here, we see that to compute the Euler function of n, we actually need the prime numbers. We need to know p and q to learn this value. And p and q are secret values. So on this slide and all the following ones, the green stuff is the private part of the private key, and the blue stuff is public. So the primes must be secret. And the private exponent is also going to be secret, and it's the inverse of the public exponent modulo phi of n. So if you remember, inverse means that d is chosen such that d times e would equal 1 modulo phi of n. Okay? So the public key now consists of this public exponent and the modulus. For the private key, we need to remember the private exponent and also the modulus. The primes are also secret, but we can throw them away actually. We don't necessarily need to remember them. It's sometimes convenient, but we don't, strictly speaking, need them. What we do need is the public and the private exponent and the public modulus. How do we use them for encryption? You might wonder how it fits on the slide, since I already filled so much of it with the key generation, but thankfully the actual encryption scheme is really, really simple. It's just a simple exponentiation. So to encrypt the message M to a ciphertext C, we simply convert the message to an integer number, integer representation. We can simply do that by taking the string and interpreting it as a number, and raise it to the power of the public exponent, modulo n. That's it. That's the encryption scheme. The decryption looks, in fact, almost identical. What do we do here? To decrypt the ciphertext C we computed this way, we take it and raise it to the power of the private exponent, also modulo n. And the result is going to be the message again. For this to work, side note, we need m to be smaller than n. Otherwise, it would be ambiguous, because if the whole equation is modulo n, then also the result is of m is modulo n. So if it would be larger than n, we would get a result that is a different representative of the same class. Long story short, just choose a message that's shorter than the modulus. Okay, so I claim that the decryption is simply the same process but with a different exponent. Why does it work? Well, it works thanks to this theorem up here. Because let's look at it. If we compute C to the power of the private exponent, what are we actually doing? Well, C was computed as m to the power of e. So what we're actually computing is m to the power of e to the power of d, which is the same as m to the e times d. What do we know about e and d? We know that they're inverses of each other modulo phi of n. So in other words, we can rewrite them as 1, because they're inverses, but they're inverses modulo phi of n, so plus some multiple of phi of n. Now what do we know about phi of n? We do know that any number to the power of phi of n equals 1 modulo n. So in other words, if I look at this, I can split it up into m to the power of 1, that's m, times m to the power of phi of n to the power of k, using exponentiation rules. But m to the power of phi of n is 1, and 1 to the power of k is definitely still 1. So as a result, I would get m times 1, which is just m. So this is the reason why the decryption process works. It's more easy to remember to simply say the exponent is the inverse of the other exponent, and this means that the function is the inverse function of the other function. Okay, so this is the RSA encryption scheme. Let's have a look at a number example. So to make it feasible to fit on the slides, I'm not going to choose 2 large primes, but 2 tiny primes. So let's pick 3 and 11. If we have these primes, then we get a modulus, which is 3 times 11, that's 33. And now it's time to pick the public and private exponents. For the public exponent, we can take any number that's co-prime to phi of n. Let's look what phi of n is. Phi of n is p minus 1 times q minus 1. In our case, that's 2 times 10, so 20. This means our public exponent needs to be co-prime to 20, and it shouldn't be 1. So we're not going to take 1, we're not going to take 2 because it has a common divisor with 20, but 3 seems fine. 3 doesn't have a common prime factor with 20, because 20 is not divisible by 3. So 3 is going to be our public exponent. You see from my thought process here that we didn't choose it randomly, but we just took the smallest e that worked, because it satisfied our criterion. Now we need to compute the private exponent. This is supposed to be the inverse of e modulo phi of n. So we're looking for the inverse of 3 modulo 20. So we're looking for a number, d, such that d times 3 equals 1 modulo 20. And this number is 7. Why? Because 3 times 7 is 21. And 21 modulo 20 is 1. So 7 is the correct answer here. That's the inverse. If we don't want to know the answer and just verify it, but actually compute it, we could use something like the extended Euclidean algorithm. Okay, so this is our key pair. So 7 and 33 is our private key, and 3 and 33 is our public key, which we publish. Now anyone who knows the 3 and the 33 can encrypt something. For example, if we want to encrypt the message 4, then what we do is, dear camera, here's the focus. Yes, no, maybe? Yes. Okay, so 4 to the power of 3 is what we're trying to compute, so message to the power of the exponent. I simply typed it into the calculator, and the result of 4 to the power of 3 modulo 33 turns out to be 31. You can easily get that because 4 to the power of 3 is the same as 2 to the power of 6, which is 64, and 64 minus 33 is 31. So that's how you verify it. Okay, so the ciphertext for 4 is 31. Now let's look at the decryption and verify that it actually works. So we take ciphertext and raise it to the private exponent. The ciphertext was 31, the private exponent was 7, and 31 to the power of 7 is a big number, which my calculator can evaluate and reduce modulo 33. The result is 4. And this is actually the same as the message we put in. That's great. So at least in our example, it actually worked. Let's have a look at the question that just popped up. It's going to be a bit hard to read on the slide, but let's see. So somebody has another advanced comment, namely, they're asking whether M has to be co-prime to N for the decryption to work, right? Well, very good question. Partly true. So the question refers to this part here. The argument that I gave was based on this theorem, and the theorem required that A and N are co-prime for this formula to work. So actually in this explanation here, I only covered numbers M that are co-prime to N. So indeed, the question is correct regarding my explanation, but the fact is the decryption actually also works for other M's, but then you need to adapt the explanation a bit. I'm not going to do that here, but trust me, it works. But good catch, never ignore the prerequisites in your theorems when you use them somewhere. Okay, so let's have a look at the security of this thing. So why is it secure? Again, we can define a specific problem that describes exactly what the attacker wants to do. The attacker wants to recover the message from the ciphertext. So that's why we say the RSA problem is you're given the public modulus and the public exponent E and some ciphertext, and your challenge is to find a message M such that M is encrypted to this ciphertext. If you guess a particular M, you can verify whether it's correct because you can publicly evaluate the encryption and compare. And let's see how hard this problem is. Again, we don't know exactly, so we don't have any hardness proof or so for this problem. But there is again the only good way we know how to solve it, or the best way we know how to solve it. And this best way is to recover the private key. And to do that, we need P and Q. So this is why we say the security of RSA is based on the factorization problem. Because if the attacker is so powerful that they can factor N, then they can recover P and Q from M, and then they can recover the private exponent by computing phi of N and inverting E. So if an attacker can factor, they can go back from this public value to these private values, and this means they can also compute this private value here. So that's why being able to factor N would mean to break the RSA problem for this particular number. We believe that this RSA problem is as hard as factoring. We don't know exactly. And we believe that the factoring problem is infeasible for sufficiently large M, where sufficiently large turns out to be exactly the same kind of sufficiently large as we had in Diffie-hellman. So in particular, we also want 3000 bits keys for RSA. In fact, the hardness of the factoring problem and the discrete log problem is very closely related. So the algorithms do have some similarities, even though the problems look different. So again, it's important that the modulus is large enough so that the fastest factoring algorithm cannot factor the number faster than in 2 to the 128 operations. The current factoring record that we have, so the largest number that looks like an RSA modulus that was factored without further properties, is this one here, so about 700 bits. And this was already quite a while ago. So it took 2000 CPU years, of course, in using parallelization. But things have gotten, so we do have stronger computers since then. So probably today something stronger could be feasible. What else do I say? So, oh yeah, so since this was already broken in practice by an academic team, you can imagine that a 1000-bit modulus, which isn't that much larger, shouldn't be used anymore. Unfortunately, you often still find 1000-bit RSA moduluses. Please don't use them. They're definitely obsolete. Please use something like 3000 bits. Okay, so this is about the security, but since we're talking about these huge numbers all the time, one thing that you might have wondered about is, how do I actually compute these things here? So it looks really simple. It looks like a simple exponentiation. But think about how large the numbers are. If m is a 3000-bit number and the exponent is a 3000-bit number, if we do this exponentiation, the result would be something like 2 to the 3000 bits long. That's absolutely infeasibly large, way, way, way beyond whatever any amount of power in this solar system could compute. So it absolutely doesn't work to first exponentiate everything, like we did in this simple nice example here, and then only reduce the result. And even doing all of these exponentiation steps individually is totally unfeasible. So multiplying m by itself 2 to the 3000 times, which we would approximately need to do for such a large exponent, is absolutely unfeasible. So how do we actually evaluate this innocent looking RSA? The good news is that there is a very simple implementation technique which allows to exponentiate even with such large numbers. It's still somewhat expensive, way more expensive than AES, like 1000 times more expensive or so, but it's at least feasible. You can definitely compute it on your computer or your phone or even smaller devices. So how does it work? This algorithm or this trick is called the square and multiply algorithm. So I've illustrated it here for the case of the decryption function. There we also have the exponentiation. Ciphertext to the power of the secret modulus. So how do we do it? Instead of taking the whole number in here, which is something like almost 2 to the 3000, and multiplying c by itself this often, we are going to take advantage of the binary representation of the exponent, which is 3000 bits long. So d looks like some strings of zeros and ones with approximately 3000 digits. How do we compute now? We're actually going to compute this step by step. So we're first going to compute c to the power of 1. Then we're going to use this result to compute c to the power of 1, then c to the power of 110, and so on. So we are going to scan the exponent bit by bit and always compute the partial result of c to the power of the first k digits. And once we've done these 3000 updates here, we're going to have the final result. So let's have a look at how that works. Let's first look at c to the power of 1. That's really easy, right? We know that c to the power of 1 is going to be c. Now let's have a look at the next digit. Let's compute c to the power of 1, so c to the power of 3 in other words. Well, we can actually use the result we already have and extend it. So if we have, let's ignore this bit for now and just look at the first one. If we have c to the power of 1, how do we get c to the power of 10? Well, extending 1 to 10 means doubling the result. So shifting the bit string by 1 position means doubling. And if the exponent doubles, What does this mean for the result? It means squaring the result. This is because of the basic exponentiation rules we've seen before. If you want to derive c to the power of 2d from c to the power of d, you take c to the d and square it. So to extend this to here, we are going to square the result we already have. So now we've done 1, 0, but we needed 1, 1. So in other words, we need one more c. But we can simply do that. We can multiply with c. And this is actually already the first part of the algorithm. Whenever we extend to the next bit, and the next bit is a 1, we take the result we have and square it. That's like shifting the exponent. And then we multiply to compensate for this times c, for the 1 in the exponent. So that's this step. What happens if we have a 0? Well, if we have a 0, that's even easier. We're now trying to extend 1, 1 to 1, 1, 0. So we simply square, because we said that shifting the exponent once to the left is simply squaring. And with this process, we can go through the entire algorithm. Whenever there's a 0, we only square the intermediate result. And when there's a 1, we square and multiply. And that's where the name of the algorithm comes from. Okay, and we do this for all bits, for all 3000 bits. So we have a total of 3000 steps in our loop. And at each step, we either square or we square and multiply. And that's how we can exponentiate to the power of very large numbers. Okay, what can we say about the security? I need to hurry a bit because we have only 4 minutes left. There is actually one issue with the basic explanation I've given so far that is actually quite deadly. And that we don't really see if we just look at the mathematical problem. Dear camera, here I am, thanks. So this problem is that the RSA we've seen so far is deterministic. That's a problem we've already seen in the symmetric case. That's why we had nonces. But it turns out that here, this determinism is so much worse than in the symmetric case because the attacker has the power to encrypt. So this means they can simply test whether any ciphertext that they intercepted matches a particular message. For example, if the attacker knows that the answer or the message that is sent either yes or no or maybe, or some other small set of options, what they can do is they can simply try all of the possible messages and verify whether the encryption of these candidate messages gives the right ciphertext. And if it does, then it was actually the message. So here the attacker has this extra power of doing the encryption. For this reason, we absolutely need to make it randomized. So it's much more crucial here than in the symmetric case. And we do this with a randomized padding scheme. And the goal is to receive what is called the security property of indistinguishability under adaptive chosen ciphertext attacks. That's quite a mouthful. You don't necessarily need to remember it, but it's good to understand the main concept. So in order to prevent this, we need to make sure that an attacker really cannot get any amount of information from the ciphertext. And verifying whether it matches a particular message is definitely information, so this shouldn't be possible. And we can formalize this as a sort of what we call security game. So a security game is always we give the attacker some challenge and they are not supposed to be able to solve this challenge or this game. So here the challenge is the attacker can choose any two candidate messages, and they know that one of these two messages is encrypted to the ciphertext C by the encryption oracle. And now the attacker should not be able to distinguish, so to tell apart, to know whether this one ciphertext belongs to message M0 or to message M1. So they cannot verify the guesses anymore. And for this we need a randomized padding scheme. There are two such padding schemes that we know. One of them is very simple, so I'll explain it, but it's also deprecated, so please don't use it. And this is called the RSAES PKCS1 version 1.5 padding scheme. What does that stand for? Well, you know RSA. This ES here doesn't have anything to do with AES, but it means encryption scheme, so RSA encryption scheme, and PKCS stands for Public Key Cryptography Standard. So it's a standardized scheme, and that's just the version number of the scheme. What does it do? Well, it simply takes the message and pads it with a random value. And this padding consists of a sufficient amount of randomness, at least 8 bytes, but it can be longer if the message is shorter. And additionally, there are some additional constants which define the version and so on. So what this means is, if you want to encrypt a message with this scheme, the length of the message can be at most key size of the modulus, so 3000 bits, minus at least 11 bits. If the message is shorter than that, then it can fill up with this method. So this is the part that can grow. If the message is shorter, we have more randomness. And with this random padding, the message is afterwards encrypted with regular RSA. There's unfortunately a very advanced attack that I can't explain here that takes advantage of this construction. In fact, it exploits this innocent looking constant here. But the good news is we have a replacement. This is called RSAES OAEP, where OAEP is short for Optimal Asymmetric Encryption Padding. It's a bit more complicated, so I don't show it here. But essentially, it also just adds randomness to the message in a particular way. Good. I had a question about the security levels, a little quiz question. We're going to skip that and do it next week at the beginning. And instead, we're going to have a very quick look at signatures. The good news is this look can be really short because we can reuse a lot of what we've already done. So I just want to mention there was a brief question, how to avoid textbook RSA, but I believe I've just shown that. So this is how you avoid the problem. Okay, so let's have a look at signature schemes. So what do they try to achieve? We also are going to generate a public and a private key. And we are again going to have two algorithms. One needs the private key, that's the signing. So Alice can sign any message by computing a signature and transmitting the signature together with the message. You already know this concept from authentication tags, except that it's now asymmetric. And asymmetric means that everybody can now verify this. So they have a verification algorithm which takes the message and the signature and answers either that's correct or that's wrong. And if it's wrong, then we need to throw away the message because it was garbage. And the usage is very similar to a Mac, except that Alice now has the private key, so the person who signs, and the public key is sufficient to verify. And what do we get? What kind of properties do we get? We get the property of sender authentication, so we definitely know who sent this message. Can only have been Alice because only Alice has the private key. We know that the message wasn't changed because nobody else who doesn't have the private key could have generated a valid signature that can be verified with the public key. And since only Alice has the private key, we also have non-repudiation, which means Alice cannot deny that she signed this message because nobody else could have done it. The security is then measured similar to the trapdoor system we saw before. So it must be easy to compute the signature if you have the key, but very hard to compute the signature if you don't have the private key. And computing a fake signature is called a forgery, like for Macs. And verifying, on the other hand, should be easy. Okay, and this can be done based on exactly the problems we know already. We are going to have a look at one example based on the integer factorization problem, because it's so easy, so similar to what we've seen before. But in the exercises, you're going to meet a system that's based on the discrete log problem. So you will recognize some things that look a bit like Diffie-hellman. And you will get a more detailed explanation, I believe, in one of the tutorials. I think this afternoon. So let's have a look at the IFP-based signature. The key generation looks exactly like RSA. And actually, the signature scheme we're looking at is also called RSA signatures, because it's more or less identical. The only thing that's different is how we use the private and public key. To sign something, we now use the private exponent, And to verify, we use the public exponent. So the reason, the fact that the RSA signature scheme looks almost exactly like the RSA encryption scheme is why people sometimes get mixed up about the terminology. So they use terms like encrypt and decrypt for signatures, but please don't do that. They really should be called sign and verify. And in other signature schemes, you don't have this nice situation that encryption and signature look so similar. So please don't expect that. In particular, the signature algorithm that you are going to look at in the exercises cannot be converted into an encryption scheme. So it looks quite different. Okay, so that's an example signature scheme. Let's have a very, very brief look at its security. There is actually one issue. Because we have based this signature scheme on an encryption scheme, it would actually be possible to recover a message from a signature. Why is this awkward? It's awkward because now anybody could invent a signature and then generate a corresponding random looking message. Now, random looking might not be so useful, but it's still not a property that a signature scheme should have. Another awkward thing is that the signature scheme is only suitable for very short messages, because we said the message must be shorter than the modulus. What if I want to sign a big document? It's not going to be less than 3000 bits. And there's a solution for both of these problems, and that is that we hash the message before we sign it. This is also called a signature with appendix for some reason. So how does it work? How do you combine this with the RSA, with the textbook RSA signature scheme? The combination is, by the way, called RSA SSA, where SSA is signature scheme with appendix. And again, we have two versions. The one that's a legacy version, it's not quite as bad as in the encryption case, but still you should prefer the newer one with probabilistic signature scheme. How does it work? So to sign a message, first you hash it using a hash function like SHA-3, and then you write this hash into the block that you put into the textbook signing scheme. So you take the hash of the message, add some bits to get the right length, and then you exponentiate it with the private key. Okay, so that's the very, very short rush through the RSA signature scheme, but you really know all the ingredients already. I guess the only new trick was to hash the message first. And this is something that you actually do in all signature schemes. Okay, so let's conclude. We're already a tiny bit over time. What did we see today? We looked at the missing ingredients to really establish a secure communication channel. The first ingredient that we looked at was to agree on a key, but based on a question we already saw that we need to also authenticate this communication. So for this reason we now have signature schemes. They allow us to authenticate each other. We're going to see how these two parts fit together in the next lecture. So these are the asymmetric handshake parts that you do in the beginning when you try to set up communication. And once you've done that, you trust that you're speaking to the right person and you have established shared secret key. Then you can do the actual communication with symmetric crypto. And we heard about a couple of schemes. All of them need 3000 bit keys at least to be secure. So we saw the key exchange scheme Diffie-hellman, and we saw that the RSA construction can be used for both encryption schemes and signatures. And in the exercises, you meet a different kind of signature scheme based on Diffie-hellman. Let's see if you have any quick final questions. And while you're thinking about that, maybe one final question from me, namely if you have any specific topics that you would like to see in the next lecture. So most of the lecture is already set, but if you have some specific questions, here is the place to edit, because this is also going to be our last crypto lecture. So if you have any wishes, please publish them now. For some reason, Menti doesn't want to show them yet. Let's see if they appear. Maybe it helps to switch to questions and back again. Otherwise, you can also drop it in the comments if you have any particular requests, in case Menti keeps refusing to actually show something here. Okay, it does show something now, but apparently you don't have any requests. Let's give it a couple more seconds. Oh, some things are showing up. So one of them, KPTI, is not a crypto topic, but you're going to hear about it in a later part of the lecture. And then there are some specific applications apparently that you're curious about. So YubiKey is one thing that's mentioned here. That could be an example. I'll have to check how complex it is and whether it's suitable for presentation in the lecture, but this could be an option. Somebody is asking about blockchain. Based on my previous comments, you might have guessed that I don't want to talk too much about it, but maybe I can have some final comments. If you're very curious about that, I think you hear more about it in a master's course called PETS, which is short for Privacy Enhancing Technologies. So if you're really into that, you can head to that course and hear more about it. And apparently people are curious about this email encryption system. So here I'm actually pretty confident that it's sufficiently easy to explain. So maybe that's one thing we could have a look at next week, because it's an example protocol that we can look at. It seems that blockchain is really popular. Okay, I need to think about what I do with that. Somebody is curious about ECC, so that's elliptic curve cryptography. I definitely do have a few comments about that. I don't have enough time to explain it in all detail. If you do want at least some of the gory details, then I would recommend that you watch the discrete logarithm lecture of the cryptography course. So it takes 1.5 hours, but that's how much time it takes to actually explain it. Somebody's asking for the Signal protocol. That's also a bit more complicated, but I think I can discuss some essentials of that. Okay, with that, thanks a lot for the inputs. Let's have a look at one final question that appeared. Apparently, my phone doesn't know about it yet. Oh, why blockchain is bad is another request. That's something I can maybe talk about. Okay, let's see. Let's hope I remember all of that, but I can just recheck the YouTube stream when I prepare next week's lecture again. Okay, let's look at the questions. Are there any organizations using their own internal crypto schemes? Unfortunately, yes, lots. There are a few areas, application areas, where people like to run their own crypto. One such notorious area is car manufacturers. So for some reason, they really all want proprietary crypto in their key fobs. So in the remote keys you can use to open cars. There have been a number of rather spectacular failures in that, because they often buy some private IP, so intellectual property, that includes crypto, and since this is private, it often wasn't publicly vetted and is thus, often has some flaws. Not always, of course. There can also be advantages of hiding the specification. It definitely does make it difficult for an attacker, but it very often goes wrong. There are also many countries who absolutely want their own standards. So these standards are then usually public, but they're not the same that everybody else is using. So for example, there is an own Chinese crypto standard, and there is a Japanese one, and there is a Korean one, and there is a Russian one, and so on. So countries also usually have their own standards because they don't want to rely on cryptography that is standardized by a different country whom they don't trust fully. So for example, they don't want to use a US standard, even though many of the US standards were actually defined by European mathematicians and cryptographers. Okay, and you will definitely find many more areas. Some people also try to run their own crypto when they do, for example, scams, or when they try to use ransomware, also where they encrypt your hard drive. So there they often also hack up their own things, and thankfully they are also very often insecure. Okay, one more question, whether blockchain works like block ciphers. No, they do work a bit like a higher level hash function. So we saw in hash functions that you always get these intermediate hashes, and by hashing them and something else, you get a new hash. Blockchains use the same principle, but they try to make it as difficult as possible to find a next suitable block. And this means it costs insane amounts of energy to actually generate the follow-up blocks. And that's the main reason why I'm so skeptical of it. Because from an environmental perspective, it's simply horrible. You do a big brute force search every time you add a new block. And for that you burn tons and tons and tons of CO2. So that's why I'm skeptical. But I can talk a bit about it next week. Okay, looks like we're out of questions. That's great because we're quite a bit over time. Thanks a lot for being so active and asking questions nevertheless. And I hope you get some interesting inputs in the afternoon session on the practicals, and you have a great weekend. So bye for now and see you next week for the last crypto unit.